For centuries, when early astronomers aimed their telescopes at Mars, they assumed they were looking at a lush, inhabited twin of Earth. In 1877, the director of the Milan Observatory, Giovanni Schiaparelli, spent months mapping the Martian surface. He claimed to see linear features cutting across the planet, which he labeled canali, Italian for natural channels. But the translation was soon misinterpreted as artificial canals. An American astronomer named Percival Lowell took this idea so seriously that he built a private high-altitude observatory in Arizona specifically to study them. Lowell spent 2 decades observing the red planet and publishing detailed maps of what he believed were vast irrigation systems built by an intelligent Martian civilization, planting the idea firmly in the public mind. The human visual system is incredibly good at picking out patterns, even when they aren't there. Looking through early, low-resolution optical lenses, the brain naturally connected natural geological formations into straight lines and infrastructure. The truth remained a mystery until the 1960s and 70s, when NASA's Mariner space probes finally traveled close enough to take direct measurements. This comparative chart shows the atmospheric pressure of Earth at 1 atmosphere compared to the near vacuum of Mars. In an environment this thin, liquid water is completely unstable. It either instantly vaporizes or freezes solid. The orbiters also sent back the first clear pictures of the surface. There were no canals, no vegetation, and no cities, only a cold, dry, cratered desert. Even with better cameras, our minds still tried to find familiar shapes in the rocks, creating famous optical illusions in the orbiter imagery, like a giant smiley face in Galley Crater or a humanoid face looking back at us. Since orbital cameras definitively ruled out large-scale life and surface water, astrobiologists realized they had to change their approach. The search parameters shrank from sweeping global landscapes down to the physical dirt itself. In 1976, a Viking 1 and 2 landers touched down. They were the first probes designed with a specific objective: to scoop up Martian soil and test it for microscopic life. The landers ran experiments searching for evidence that microbes were consuming nutrients. In 2 tests, measuring carbon assimilation and gas exchange, the soil gave distinct positive responses, acting exactly as if living organisms were metabolizing. But those results conflicted directly with the onboard mass spectrograph. That instrument searched for organic molecules, the carbon-based building blocks of life, and found absolutely zero. Even at detection levels 10 million times lower than Earth, the soil was sterile. Scientists eventually deduced that the apparent metabolism was likely a false positive. The Martian soil contains strong oxidants, like iron peroxide, which can trigger harsh chemical reactions that perfectly mimic the gas release of living microbes. Without direct visual proof of a cell, basic soil tests are ambiguous. Inorganic chemistry can easily masquerade as biological activity, making the search for microscopic life exceptionally difficult. The search for life moved from the Martian surface back to Earth with ALH 84001, a 4.5 billion-year-old Martian meteorite discovered in the ice of Antarctica. In 1996, an analysis of the rock found magnetic crystals, similar to those produced by Earth bacteria, as well as microscopic shapes resembling fossilized nanobacteria. Then, in 2004, ground-based telescopes detected trace amounts of methane gas floating in the Martian atmosphere. This equation shows why that observation was so startling. On Mars, methane reacts with oxygen to form water and carbon dioxide, breaking down completely in about 300 years. Because of its short lifespan, the methane we see today cannot be left over from billions of years ago. Something must be actively producing it right now, whether that is a geological source like a volcano or a biological source like methanogenic bacteria. While the search at the molecular level provided new evidence to investigate, the results remained short of the undeniable, conclusive proof required to confirm biological activity. Today, the astrobiological strategy has shifted. Instead of trying to detect life directly, scientists focus on tracing the history of water. Recent missions have uncovered a dynamic chemical cycle on Mars. We found subsurface water ice and detected perchlorate salts in the soil, a strong oxidant that effectively lowers the freezing point of water, influencing the planet's humidity. This is why modern rovers, like the Mars Science Laboratory, are built to land in dry, ancient riverbeds and carry out extensive biochemical audits of the terrain. They are no longer running simple metabolism tests. The current objective is to meticulously catalog deep surface mineralogy and build an exact inventory of whatever organic compounds might be hiding in the rocks. Processing that overwhelming amount of planetary data requires a massive, sustained human effort, analyzing chemical readouts from millions of miles away. The target for finding life on Mars has steadily shrunk, from the vast imaginary canals that captivated the public down to the microscopic traces of elements buried in the dirt. We had to trade the hopeful eyes of a 19th century astronomer for the rigorous, precise tools of a modern chemist.